this, we'll obviously let them in. So, warm welcome. My name's John Richardson. I'm the Head of Innovation at SGN. Today, we've got the event which has been hosted by both IGEM and the Pipeline Industries Guild. And it's an introduction to RRES. Now, RRES is the Robotics, Roadwork and Excavation System. That is a NIC project through Ofgem funding, and it's been delivered by ULC and SGN. If we move to the next slide, guys. So one of the reasons that we're all here on this call doing this virtually, the RRES platform, and Ali and the team from ULC were supposed to be over for Utility Week Live. So obviously due to the current circumstances, that can't be achieved, unfortunately. So we actually agreed and decided collectively between all the parties involved that this would be a free event. Obviously try and get the interest, get as many people on as we possibly could. But there's also, you may have seen it in the invites, there's also a recommendation, if we can, to make a donation of £10 to NHS charities together. And if you don't have the details, I think after the presentation, we can send a link along to that website. Okay, thanks. So speakers today, not necessarily a speaker, I'm doing the easy job, the introduction. So mentioned it earlier, I'm Head of Innovation at SGN, relatively new to the gas distribution networks, just over about 15 months, but certainly a lot of involvement in the pipeline industry before that. We've also got Dr. Ali Asmari from ULC. And Ali is the project engineering lead at ULC Robotics, as well as the project lead for this project. We've also got Ollie Machin, who's the RRES project lead at SGN. Okay, I mentioned it earlier, so this has been hosted by IGEM and the Pipeline Industries Guild. A big thank you to IGEM, particularly David McLeod at ULC, who made the offer to make this a joint hosted event. So just for information, we're trying to rejuvenate the Pipeline Industry Guild Scottish branch. So this is a good opportunity for us to raise a little bit of exposure for it. And the presentation material and the project will be done by SGN and the ULC collectively. I mentioned earlier that we would actually do a suggested donation of £10 to NHS charities together. Again, we'll get that information across to you guys as soon as possible. On to the agenda. What we'll do after my brief introduction is Ollie Machin from SGN will give you a background to the project, where it came from and why, as well as some of the main benefits that we would foresee going forward. We'll then move on to the project overview by Ali from ULC, and then there'll be an opportunity at the end of the presentations for a Q&A session, which will be facilitated by Simon from IGEM. And what I would suggest is if there's any questions that pop up during the presentation material, if we could please even just put them in the chat screen, and we'll try and facilitate the questions that way. And again, apologies if anybody's seen my youngest son trying to get into the screenshot there, but I guess that's a sign of the times at the moment. So we'll pass on now to Ollie Machin, who'll give you an idea of the background. Thanks, guys.
Thanks, John. Yeah, I'm not going to take up too much of the time. I want you, I really want to get into the nitty gritty of the engineering. I know that's what you guys are really here for, but I just wanted to give you just a bit of the background as to why the project exists and where it's come from. So some of you are probably aware that during Rio, Ofgem introduced 2 funds to stimulate innovation in the gas networks. the first one was an NIA, which is Network Innovation Allowance, which ring fences part of our turnover that we get to use for innovation projects. And the second fund is the NIC fund, so the Network Innovation Competition. And basically that's a £20 million pot that that Ofgem have allow us to target projects with a safety and particularly an environmental benefit moving forward. And so these are sort of for big transitionary projects. We've had a fair bit of success with NIC. The project's quite old. We're in 2020 now. We actually started work on the project in 2015, 2016, and what we were doing is using the NIA pot to create low TRL projects that created supporting evidence for why RES could exist. And you'll see when Ali takes you through some of the technologies why it was essential that to take a convincing bid to Ofgem, it needed we couldn't have started at like TRL 2 or TRL 1. It needed to be quite mature for the panel to be able to award the funding and have some confidence in what we were doing. So we spent, like I say, a year and a half putting evidence together. We entered a bid in 2017. For those that know, the NIC bidding process takes about a year to go through. And we won that bid. Obviously, you're here to see the project, and that was awarded 6.3 million in funding. It's a 7.3 million total project budget, and we kicked off in April 2018, and we're due to finish March 2021. Like I say, it was SGN's fourth successful NIC project, and actually our second one with ULC Robotics. We'd previously undertaken a project to create the RRES robots, which work internally on the network to remediate joints. So what's the project about? So RES, roadworks are they're a disruptive, quite aggressive activity. All right, so what you'll hear is, you're going to see a lot about robots and AI, and you read in the media, robots taking over people's jobs. The real point kind of I want to stress is I really don't believe, and we don't believe that, remuneration shouldn't be about somebody, expending their physical presence, degrading themselves for reward. And so anywhere robotics can step in and allow that person to actually make judgment decisions is really positive. So what we wanted to do is, on behalf of the workforce, enhance their safety. We wanted to lower the damage risk to the assets. As you know, cable strikes and things like that can be hugely hazardous. We wanted to have an effect on disruption. There's a lot of pressure now, particularly in London from TfL, rightfully, for us to work more efficiently. And we had the opportunity to reduce the CO2 footprint at the same time. RES is an all-electric system. And the other thing it starts to do is to bring a degree of consistency and repeatability around what you can then conceive as routine operations. If you're doing a job, we can do it pretty much the same every time with a high degree of confidence if we have the right system. And the other thing to know, and we made Ofgem aware of, is if it works in one utility, and then it's highly likely to work in other utilities, and actually it'll be applicable across other sectors. Okay. Do you want to pick up, Al?
Yes, absolutely. Good afternoon, everyone. Thank you, John and Ollie, for the introduction, and thank you all for taking the time today to attend this webinar. My name is Ali Asmari. I am the program manager for the robotic roadworks at ULC Robotics. Today, I want to take you through some of the technical development that we have done in the past 2 years under this project. And at the end, we're going to finish it up with Q&A, and hopefully toward the very end, we'll give you guys a demo of the robot in action. I want to start my presentation by talking about the robotic platform that we have developed for this project. The core of this system is a 6 degree of freedom robotic arm that you usually see them operating in manufacturing facilities in a very known environment, doing routine operation like welding or moving specific parts from one spot to the other. They're mostly behaving very accurately in a completely controlled scenarios. What we have done is we have taken that robot from indoor use, put it on a track platform, make it mobile, provided with proper power and control system so that we can take this to these basically unknown environments, roadways, and conduct the same routine operations, but adding a little bit of smart through AI and machine learning so that the robot would be able to take this kind of like a risky and dangerous work from the operators and providing them with better tools to conduct this operation more accurately. So here you see kind of like a breakdown of different components of the robot. As I said, the 6 degree of freedom robotic arm, a fully electric power system that can last for about 8 hours of operation minimum. And then the system is mounted on tracks, so it allows the robot to go on different terrains, and everything is covered by a waterproof cover that would allow the robot operate in different weather conditions as well. Now, the idea is to create this kind of like an open source mindset development kit that is capable of doing all this operation in new environment outdoor, and then later developing new tools and end effectors for this robot arm to use them, articulate them properly, and automate different routine tasks. So under Robotic Roadworks excavation system, our purpose is to automate this excavation operation end to end, starting by scanning the ground, identifying the locations of the assets that are under the ground, then cutting the road surface and removing a core from the ground. The next step is agitating the soil, the column of soil that's above the buried assets, and then removing them. And once the buried assets and the pipe is exposed, getting the robot to conduct operation on the pipe, such as installation of a fitting, installation of sensors, or doing any type of repair work. And once the work is done, a recycled material would be put back in, and the same core that was taken from the road surface would be reinstated, hoping that this entire operation can be done autonomously to some point with minimum supervision from the operators. Now, I'm going to take you through like different technical aspects of each tool head that we have designed and created for this robotic platform. To start off, it's sensing the ground. Prior to any excavation, we use a suite of different sensors that the robot carries above the ground and then collects data from above the ground. So under the project in the past 2 years, we have done extensive research in all the sensors that were out in the market, any sensors that had a proven track record of identifying different types of assets under the ground. Went through different capabilities, pros and cons of using each, and then created a combination of these sensors, put them in one tool head that the robot would eventually pick up and pass it over the ground in the area of excavation, as you can see in this video, and then collect the data from the ground. Right now, the robot is going through a patent pending procedure that we have developed with as I said, a combination of different sensors, ground penetrating radar, electromagnetic waves, and at different frequencies, collecting it in a specific routine and providing that data set for the operators to eventually make decision about the condition of the ground as well as the locations of the assets. One of the main benefits of using the robotic system rather than manually collecting the data is the accuracy of the robot arm, which allows us to basically overlay data collected from different sensor technologies on top of each other, knowing exactly what every single data point, where every single data point was collected from. And then by overlaying all of them together, we would be able to have more precise, accurate maps. And then with this accuracy, the robot can collect much higher resolution data. So Once the data collection is done, usually the big challenge is what do you do with the data? These are like super technical information that a typical operator that's conducting the operation is not able to make sense of. So we have developed computer algorithms that autonomously process all this data that's collected from different sensors from different locations of the site, process them and fuse them all together, trying to generate a 3D map of the assets under the ground. So here is one of the models, one of the renderings of some of the recent work that we have done, is basically the data that's been collected by the robot, processed autonomously, turned into 3D contour maps, so that the operator would be able to basically just interact with this type of map, identify the locations of the target asset, as well as getting an understanding of the environmental condition around the area that we are doing excavation, to be mindful of hazardous networks like a high voltage cable in the vicinity of operation. So once the sensing is done, the target asset is identified, and we know the location to conduct the operation. The next step is cutting the road surface and exposing the soil. So under the project, we have fabricated a custom road cutting device. This would allow the robot to basically pick up this tool from its tool set and then articulate it in different patterns and create different shapes of cuts on the road. So we are not really bound by a specific size or a specific form factor for cutting the road surface. Using this tool that you see in this video, the robotic arm can cut not only circles, but it can also cut oval shapes from the road surface. So the idea of cutting Olympic rings, if you guys are familiar with, that basically creating a pattern of multiple round cuts together to expose a wider area for excavation is completely gone now. The robot can do any form, any size, any shape, cut it out of the ground. And then using AI, the robotic arm is sensing the amount of load that's being applied to the ground and to the material. So in real time, it is making adjustments on the trajectory that the cut is happening, also tweaking the amount of force and load that's being applied, which will increase the lifetime of the tool itself, as well as optimizing the operation. So when we have to cut, for example, through a reinforced concrete deck, the robot can slow down when it's hitting a rebar and cutting through a rebar. And when the material is soft, it can speed up and do a much faster job and finish the job much quicker. We can also accurately control the depth of cut. So we know exactly how deep we need to cut before potentially causing any damage to the assets. Under the project, we have also developed other tools that would allow the robot to drill a pilot hole from the core, for example, a 75mm pilot hole that would give the operators more understanding about the condition of the deck, as well as the depth of the cut that needs to be done. The pilot hole can also be used by the robot itself as a grabbing point to remove the core from the excavation site. So here you can see the robot took a core, the operator can assess that, and then the same pilot hole can be used using obviously a different tool. The robot can easily pick up that, as you see in this video, the oval shape, or we call it an airplane window. It's kind of like an elongated circle or a rectangle with round edges from the ground that would allow us to conduct a wider operation. So the core is removed. Now the layers of soil above the buried assets are exposed. As you guys might know, vacuum excavation is being widely used in the industry for exposing buried assets. But one of the big challenges is agitating the soil. VACX units can suck up everything that's been agitated. But currently, the way the operation is being done is heavily dependent on manual labor. It's an operator with an air lens that tries to basically identify the locations to target and then agitate the soil in tangent with the operation of the VACX unit, trying to remove different layers of soil. And this is one of like the relatively dangerous operations that if you don't have proper insight or if you don't have the right skill sets, you might potentially damage an asset that existed under the ground and we didn't know about. So under the project, we did an extensive research on development of supersonic air nozzles that would optimize the amount of agitation force that the compressed air can create. Then we integrated all these supersonic air nozzles within a tool head that the robot can again pick from its array of tool sets and then articulate it in the area to not only agitate the soil, but also remove them once they are polarized. So here in this video, you see the operation being done fully autonomously by the robot. What we have done is just set it up for the robot, identify the location. And what the robot is doing is using these supersonic air nozzles, blasting the air in different spots, in different orientations, agitating them, polarizing the soil, and then the vacuum unit that's going through the tool head is basically sucking up everything that's been agitated. So as you see, the robot is removing the soil layer by layer, descending the tool further and further down inside the hole. So in this video, what you saw is we excavated about 5 to 6 feet, up to almost 2 meters deep, at a highly compacted virgin clay soil that we did this trial in. The other thing that I want to mention is the use of AI in improving the safety of the operation. So this robotic arm that we have is able to measure the amount of load and torque applied to the end effector at any point. So in case the tool head comes in touch, first of all, we're using compressed air not to cause any damage to the assets when we are agitating the soil around them. But in case we miss a buried asset that we couldn't identify through the sensing, and the end effector comes in touch with the tool, the robotic arm will sense the amount of load that's applied and the torques in different directions, identify this impact, and right away pull back and raise a flag for the operator that there might be an anomaly in this hole. And then the operator can supervise the operation and avoid any type of damages to either the gas pipe or other third-party asset that might be in the vicinity of the excavation hole. So the excavation is done, and as I said earlier, we are doing this operation in a completely unknown environment. So the robot itself needs to be aware of the obstacles in its vicinity, or once the excavation is done and the assets are exposed, the robot needs to have an understanding of how deep these assets are or where it is exactly to conduct operation on it. So we have developed using computer vision and AI. We've used a series of different sensors, integrated them within one tool head for the robot, that the robot can create a perception map about its environment and about the area that it's about to conduct operation in. So here, what I'm going to be showing you in this video is we installed this tool head at the end of the robotic arm. The robot is housed in our shop, and then this robotic arm is circling around the room, looking at different spots using the sensors. Now, as different parts of the room become visible to the field of view of these sensors, the robot arm measures the distance of every visible point to its center, creating a point cloud, or basically a 3D perception map of everything around it. So as this robotic arm is moving around the room, it's kind of like looking at itself. It's looking at the walls. It's looking at the operators in the vicinity and creating all these obstacles that it's not supposed to bump into. So later, this point cloud, which is which also has color information, can be used to basically identify not only the obstacles, but kind of like tell what is that specific obstacle that we are interfacing with. Is that a plastic pipe that I'm working on or a metal pipe? And kind of like providing this information for future development of other tools to conduct operation on the assets that's been exposed. As I mentioned, there is very accurate measurement that can happen doing volumetric measurements of the excavated hole to, for example, account for the amount of recycled material that needs to be brought back to the site for reinstatement. So the excavation is done, 3D model is created, the asset is exposed. The next step is to conduct operation on these assets. Right now, we are in the process of developing tools to basically prepare the pipe and do installation of a fitting on a gas pipe. And this is kind of like the start. This is the proof of concept that a robotic platform is a meaningful tool to basically conduct all of this operation end to end with minimum supervision and intervention of an operator. This basically opens up the door for other industries, for other networks, for electric networks, water networks who have assets buried under the ground, as well as gas companies who always do these type of operations, and developed other custom-made tools that can facilitate some of the operation that they need to do. So bringing the operators out of the danger zone. Once the operation is conducted on the buried asset and everything is completed, now it's time to reinstate the backfill material, the recycled soil in the excavation hole, tamping it in place, and then preparing it for reinstatement of the core. So what we have done here is we have integrated an air compactor into a tool that can also be picked up by the robot arm. As you see in this video, what the operators are doing is they're basically just pouring backfill material, recycled soil into the hole, and then the robot, having approved compactness sensors at the bottom of the hole, will measure the amount of compactness of the layer of the soil that's put on top. It will compact it until it reaches the requirements of compactness. Once that layer is done, the robot brings the tool further up, and all the operator needs to do is just supervising and providing the backfill material to the system. The robot, as you can see in this video, can autonomously compact the entire thing, knowing the footprint of the area that's been excavated, and prepare the ground for reinstatement of the core that's been already taken from the road surface. So at the end of this, the core that was excavated using the same tool will be picked up and will be placed back into the excavation hole with proper bonding material around it. And that's the end of the operation, from beginning scanning all the way to reinstating of the ground. Now, as Ollie mentioned, this is a 3-year project. This phase of the project is about 3 years, and we are 2 years into it. We have still another year left, and in the coming year, we are working on different aspects of autonomy for the operation. Obviously, as you saw in these videos, most of the tool sets are already developed. Now we are doing more field trials, more testing, and by further integration of software and hardware, we are creating more capabilities for the system. We are creating more AI algorithms that would allow the robot to make decisions on the spot. We are also developing any necessary support equipment for transportation and deployment of the robot, eventually in the UK. That includes means of transportation for the robot, storage of the robot, and providing anything required to have basically the entire operation done at the site, be it from VAC-X unit, compressed air, or even a charging station to charge up the robot between 2 days of operation. We're working on other end effectors to conduct operation on the pipe, prepping the pipe, installation of a fitting, as I explained earlier. And then the target goal is to bring the robot to the UK in early 2021 for field trials of this entire end-to-end operation. We are also collaborating with SGN to further develop every single technology that we were able to create under this project, and potentially spin them off into a variety of products. So the sensing capabilities and the sensing, the software package that we have developed for creating a 3D model of under the ground can be turned into an independent kind of like a product that can provide services to one part of the utility industry. The cutting tool itself, the excavation head, these are all kind of like independent developments that can turn into independent products, as well as being a part of the tool set that this robot currently has for its operation. So we would like to engage with industry subject matter expert to hear about their needs around excavation and in general any type of operation that can be automated in outdoor environments, and potentially develop custom-made tools for those operations to fit their needs. Yeah, at the end, I again want to thank you all for taking the time and attending this webinar. I would like to open it up to questions, and toward the end, I will take a camera to where the robot is in the shop and give you guys a quick demonstration of the robot itself in action.
Thank you to Ali and Ollie. It's Simon here from IGEM. I'm just going to manage the Q&A session. To give Ali a chance to go in and check out if the robot's fine to work on, I'll pick the first question and throw it at Ollie. Obviously, this is a partnership approach between yourselves and ULC, and it clearly has applications across the wider utility sector. How easy do you think it's going to be for other gas networks and even other utilities to adopt this technology within their own operating procedures? Because I know it's one of those things where a great project working in one GDN doesn't necessarily always transfer over so easily to others.
Yeah, absolutely. We've designed the system, as Ali was saying, to be incredibly open about how tooling is developed. We're pretty confident that that some of the things that we're doing with the robot and the robot really fits with our strategy of trying to move all work to keyhole, basically. So it's not just bringing the robot in to undertake works that perhaps are already happening in the same way.
It's set, right?
I think what will be attractive, particularly to the gas networks, is that it offers a new way to think about how work works, and where you have a niche need, then you'll be able to work with ULC to develop a tool for RRES that will fulfill that need, and that's really where it's going to come into its own across the other sectors as well, particularly water, I think, and electric. So yeah, it's shared learning and open to all.
Okay, so there's a couple of questions around sort of working in congested trenches and the size of the robot. So obviously, it is quite large. Has there been any thought given to reducing the size to get it into more restricted areas?
I'll be completely honest. This size was the hardest part of how to develop this thing. Its size is bound by a lot of different factors and constraints. It is the size it needs to be is the kind of short answer to the question to get the core work done. We're pretty confident we'll be able to take it to most places. It has a really good reach on the arm. You may not have seen that from the videos, but it's a good 2 meter reach in different directions. So we're pretty confident that we can quite radically reduce the footprint of normal works or works that you'd commonly see, and not using keyhole methodology. We've designed it to fit pretty discreetly into a lane and to be able to very quickly execute what it is that we need it to do and then get back out of there. So yeah, its size is utterly governed by it's too numerous factors to note, but it took a fair chunk of time to work out exactly the configuration of the kit, and it's what it needs to be at the moment. It won't be different sizes of it. I can't envisage.
Okay. A couple of questions, I don't know if it's for you or for Ali, if he's back around, in terms of what is actually the robot is capable of detecting. So, question is, obviously, can it detect PE pipe? And also, would it know if it cut through a telephone cable? Because obviously they're typically buried a lot shallower than gas and electrical pipes and wires.
Yeah.
I'm also back, guys. I don't know if you can.
All right, cool.
I don't know if you can hear. Yeah, Ollie, go ahead, and then I'll take on.
Yeah, I'll do that one, and we'll switch you to your camera somehow in the background. But yeah, thanks, Simon. So I saw another question there about using maps, existing maps and things, and that kind of ties in with it. Yep. We made the decision up front to not have to use. We didn't want to. Well, we did the maths actually, and said, what does it mean if we try to use the existing mapping data, knowing that quite often that data isn't a true representation of where things are. It's the historical record of where things were drawn using the datums they were drawn against and all that kind of stuff. So we actually worked out that it would be more complex for the AI to work out how to lock against those kind of maps than it would just to develop a sensor suite that could detect everything to a high degree of tolerance and then map those for ourselves in a completely fresh way, so the users on the ground can still have the mapping system. But what RRES will do is with its suite of GPR sensors down to about 12 inches and probably 18 once we finished, it will create a pretty perfect 3D map of everything under there. So PE it picks up. The PE is interesting actually. When we were doing the hyperbole analysis through the machine learning, it actually worked out what was PE and what wasn't. We thought we'd have to train it, but it turns out that when you put hyperbole from GPR through AI and machine learning, you actually get like a double hyperbole that the AI recognizes quite sweetly as plastic, and to a degree, filled plastic as well. And I think there was a question about cables. If RRES detects cables in a shallow vicinity, the decision will be made whether to cut to and around that cable, or for the user to intervene and do it manually in a different way. So it's designed to know exactly where everything is and basically not go near it. If there's something dangerous, then it's probably to the user to decide how to proceed.
And one thing that I wanted to add is, like, this is a platform that's developed for conducting these operations. The more we collect data, the more we use this system, we're going to gain more knowledge of the conditions that we're going to be operating in, and that can be fed back into the development process, the AI algorithms for creating these maps better and better and improving their accuracy.
Thanks for that, Andy. Picking up on the sort of AI, one of the questions is, what AI services are you utilizing? Are you using things from AWS or Microsoft or Google, or which particular services maybe you accessing?
We are currently using any platform that you can name freely. That was like one of the things somebody once asked me, what is the main software language that you're writing the codes in? I was like, I can't name a language that we haven't actually used. I don't think there's any platform that we haven't really tried or we haven't used. Mainly storage of our data is on AWS platform. But as far as processing capabilities, we are pretty much using any services that are out there.
Okay. The next one's around the sensors in terms of the sensor suite. And the question is, are you using either seismic or vibroacoustic sensors as part of that?
We have looked into those sensors. The challenge that we have had with acoustic systems was that they are not, their resolution is extremely low, and that the deployment of these sensors is very time consuming. Here we're talking about assets that are buried about like 3 to 6 feet deep inside under the ground. And using acoustic, you have so many layers of noise. And based on our lab tests and the shop tests that we did, one of the things that we did when we were evaluating all these sensors is we created mock roadways similar to exactly the real life scenarios, and then try to use all of these sensor technologies, all of these different products to identify the locations of assets. And acoustic was one of the sensors that had a high level of noise, and it wasn't as easily deployable as we have with ground penetrating radar and EM sensors.
Okay. Question about how the data is processed from the sensors, and obviously, you know, we've talked about AI and a bit of machine learning. Could you just expand a little bit more about how the data is sort of processed and how you then continue to improve that process?
So the data, if the question is specifically about below ground sensing, the data is coming out from the antenna, and then a central computer is basically collecting all of this, and then every single data point collected is basically now geotagged with the accurate localization of the robotic arm. So we know exactly the locations of every data point. The next step for us is to filter out the noise level that's within each of these data sets, and then overlay them on top of each other, and then do our processing. So in a sense, we are increasing our resolution in the data when we're doing our processing by just adding more and more layers of data, combining results from different sensors, such as fusing GPR with EM.
Okay, so on a sort of similar vein is, sort of touched a little bit about using existing asset records. Does it also look for physical signs on the ground? In other words, if there are scars in the road, or perhaps the makeup of the soil, and doing the excavation process? And do you then combine that? So
that's a
combine
very
it with
good
the sensors?
question. Yeah. One of the things that I mentioned earlier is we are hoping to get this system as autonomous as possible. But currently, it's kind of like an interactive operation between an operator and the robot. The robot provides certain maps, let's say by scanning the ground. Now the operator has that 3D model that the robot has generated. The operator also has access to the available maps from the area. So he can do a comparative analysis side by side. Does this make sense based on all of the information that we had before? Or for example, I am seeing a specific pipe here. Does it match with the valve box that I see on the ground? And these are like the cues that the operators can easily pick on and then feed it into the robot. So as we add more and more of these instances and more of these information, then the model would be able to down the road use that experience of the operator and make decision on its own.
Okay. So a number of sort of observations and comments around what do you then do with that information, and what opportunities there are to share that information once you've actually got it. So whether it's about the soil type, whether it's about the precise location of buried assets, question about have you engaged with the UK Geospatial Commission to see how your survey data can improve their records, and also how do you just improve generally the records of the asset owners?
That's a great point, and I think Ollie probably can expand on that better. We are open to all of these collaborations. Yeah, Ollie, you want to take it?
Yeah. So we're tied in with projects like Lua in Greater London as a company. We recognise that our asset records, like I said earlier, are effectively an accumulation of all the historical information that we've ever had, and with the datum, you know, datum changes that have happened with locations, you know, OS moving to master map and GPS outside of sort of triangulation. We recognize that as we go along, we'll be able to bring that data together and then provide it to not just to ourselves, but to the initiatives that are going on to enable this stuff. And we're working on other projects as well to and like Ali said, there's potential to break out this sensor suite into something not related to RES to utilize and maybe speed up and make much more efficient that kind of data collection and scanning process. So yeah, it's definitely going to be of value, not just to us, but for the assets around, you know, and we'll provide the information back so that those owners can make decisions around that as well. Maybe, you know, wholesale decisions around assets that are running down the road. But yeah, it definitely needs to all be fed back. That's just, and that's part of the responsibility we kind of have to each other anyway.
So moving away from the sensor specifically, in terms of actually how the robot actually works. So probably going to link three questions.
Sorry, real quick. I'm actually right back in our shop. And you can hear probably the loud noise from the cutting tool. I'm gonna take my camera real quick through the shop to where the robot is, give you guys a quick demo of the operation, and then I'll bring it back, and then we can carry on with the Q&A for the remaining of the time.
Yeah, good, cool.
All right, sorry if it was a little loud. That was one of the closest that I've got to that tool, actually. I'm now walking back to the conference room so we can carry on with the rest of the questions that you might have about the system.
Okay, thanks, Sally.
No problem.
So I was going to link three questions, possibly if Ollie can answer in the meantime, which is about the operation of it. So sort of moving away from the sensors, but how does the machine work in clay? And it's sort of, that seems to be a perennial problem for a lot of people. How accurate is it in terms of compacting around covers and frames? And how does it cope with digging a trench or indeed a larger excavation or something which is wider than its own footprint?
Yeah. So yeah, clay is the nemesis of GPR typically. It's our target material for GPR, so we're pretty confident. We took samples of clay from our sites and created setups to test that suite of sensors. We're pretty confident we found a way through the issue of clay. What we're trying to do, we're just chasing the nines on it to make sure we've got the degree of assurance that we'd want to be able to do the cut. The excavation system's been designed specifically as well for clay. Effectively, what those hypersonic jets will do is sort of chunk it into pieces. They're intelligent. They chunk it into pieces to vacuum away. So clay was our kind of target material in terms of below the ground, and concrete with rebarring was our kind of target material for cutting. So yeah, we're pretty confident about it. Time will tell. We need to go and do some real holes in some real places, and we'll be doing that probably on our holder sites, our decommissioned holder sites. They provide a great wealth of below ground assets that we can mess about with. But yeah, that's time will tell on that one, but we're pretty confident we've got that one right. And kind of the same goes for the next part of that. Can it work around things? It will do. We hope it will do. It should be able to. It certainly won't from the start, but that's where we can only do so much in terms of training it with the AI. What we need to do is to go through the pilot program and give it as much real world experience as we can, because that's what will really refine it down to where you'd want it to be for pure autonomy. But as Ali said, for a while, it will be somewhat of a symbiotic relationship between the operator and the system, as they both learn, how this thing's going to work. But yeah, we still got a year left of what we can give it and trials to do. But yeah, as we do the real stuff, it'll start to become much more capable. Was there another part to that, Simon?
No, well, there's a supplementary which somebody's dropped in whilst you've been speaking, which was, do you actually know how deep you can sense in clay?
Our sensing right now goes to about 6 feet, about up to 2 meters. And again, this is like a very relative thing that we are talking about. Quantification of the depth of penetration, obviously based on the type of sensors that we are using, they're set to collect data from as deep as 5 meters, 4 or 5 meters. But realistically, when we are talking about clay, there are different types of clay. And then when we're talking about soil, there's moisture content in the soil that can affect all of this depth of penetration. So we are talking about a very kind of like a number that's very dependent on the environmental situations. What Ollie was mentioning earlier is like we collect more data. And right now we have set our target. We know that the clay is the biggest challenge. We have set our targets. Most of the environments that we're doing our trials are from sensing or excavation. Our majority of them are hard compacted clay. So we are aware of the challenge and we are trying to optimize it. We're trying to collect as much data as possible to figure out what is the right procedure. How do we make sense of the sensor data when we're collecting it from moist clay compared to dry clay? And then adding all of these feature sets to our data processing capabilities to make it better and better. And obviously the more data that we collect once we bring it to the UK and do actual field trials in the UK, it would make the system better.
Getting to the last few questions, which I'm sure you'll be pleased to know. Question around sort of trying to get a little bit more detail of what kind of pipe operations could the robot achieve, or that he might hope to achieve. And an example given is, could it possibly install an under pressure connection or not?
I would like to say that hopefully everything can be automated with the robot. I mean, the main reason that we developed this robotic system is to take the operators out of the risky environment. And I have to say the robotic arm is as accurate as a human operator. It has all the sensing capabilities. Obviously, it doesn't have the same understanding and same agility of the operator, but the goal is to identify like the biggest challenges, I guess the low-hanging fruits, the things that can easily be automated. Start from there, develop a tool, get the robot to validate that. And that's what we have done. We've started by cleaning up the pipe, preparing the pipe, and installing a simple fitting on it to open up this door for further integration, further development to create more and more complex tools.
Okay. I'm going to put the next two questions together because they're about time and cost. So a cost, what is, how economical would it be to rent it? And then the second one is sort of around cost and operation. So in terms of time, for the robot to complete its operation, how does that compare with traditional methods? And linked to that is how many people do you actually need to operate the robot?
I can talk on the operation side real quick. So time-wise, we are improving it to a point that the system is as autonomous as it can get. We are planning on having at least 2 operators around the robot as we roll it off and start doing the trials. And their task is really not to completely conduct the operation, but rather supervise the operation and assist the robot in the times that we need it. So that's one thing. And then the other item is that we would like to make sure that the operators who are conducting the operation are properly trained. So that's one of the other curriculum that we are putting together is training material for the operators that can take the robot to the site and efficiently conduct the operation.
And if I pick up, I pick up the other part of that, the commercials, more likely be offered as service. So work with a company to work out how to do particular operations, and then sort of change the game a little bit in how you think about how your program works. You know, this thing will be able to go in, do works, and get out in hours, really, once it's fully efficient. Rather than you going through the planning process, shutting lanes down, getting up, you know, setting traffic management up, all those kind of tasks you go through, getting reinstatement guys ready for the day after you do your job. So there's definitely going to be efficiency there. Again, it's down to the pilot and the learning of the system to get it to that efficiency. But I think most likely it has a potential to sort of change the way we think about what we're asking people to do on the ground, because it can do it so differently, so much more quickly. And basically, I guess, you know, having a price per particular type of job and thinking about how you call that in is the most likely way that it will go long term, in my view.
Okay, thanks for that.
Yeah,
I'm just going to ask one.
Sorry, Simon, just to reassure, it's normally the first question we get asked as an innovation team, you know, how much is this going to cost when it's commercialised? And just to reassure the team and probably answer a previous question that I've seen on the screen, you know, SGN and ULC have got experience with these types of projects. If you look back 6-7 years ago when we started the development of SysBot, we had the same questions asked of us, which is a robotic platform which seals leaking joints. If you look at the recently published business plans for GD2, you'll see the uptake on how we've used SysBot within SGN's 2 networks, and the uptake recently by Cadent, and I think it's working in 3 or 4 of Cadent's networks at the moment. So we have got experience in that, and as Ollie says, we're working on that in parallel with the development of the technology.
Thank you for that, John. So one final question, and I'll post it to both Ollie and Ali, and you can give me one answer each. What have you learned on the project so far that you didn't anticipate from at the outset?
You go, Al.
The excavation of operation is a big undertaking. It's a very challenging operation. I mean, I love the challenge. Don't get me wrong. It's one of the best challenges I've ever dealt with. And there's so many variables and unknowns that when we are talking about robotics and the robots automating the processes, there's so many different details, so many unknowns that you need to define for a robot. And we are taking it one step at a time.
Yeah, I think from my perspective, you know, and Ali is engineering focused, right? So you're going to get that from him. But from my perspective, you know, when we started the project, I was expecting to be over there in New York with these guys, probably about, I don't know, a third of the time, to be able to keep in touch, to be able to do what we need to do. But actually, it's, as COVID has shown, the progression of the technology that allows you to project manage and to undertake tasks collaboratively now is just phenomenal. There is no reason you cannot work with international companies on big projects and feel like you have to give up part of your life, you know, to commit to it and do it. So you can very, very easily now collaborate on major stuff online. It's just a message out there to everybody. Don't worry about taking stuff on. You don't need to be in contact all the time now. This is working fantastically, and I didn't anticipate that. I didn't anticipate being able to keep in touch and up to speed with Al and the engineering team as much as we do. When I've been out there probably 3 times now, we'll go out 4th time at the end of the year, and then RRES is over here, and we're doing the testing. So yeah,
that's brilliant. Thank you very much. So thank you to John for introducing the session. Thank you especially to both Ollie and Ali for your great presentations. The level of interest I've seen from the chat is exceptionally high. So thank you both. Just a reminder to everybody that's on the call, we have been recording it, and obviously we will make that recording available to you in the next few days. Thanks to Katie and Catherine at the Pipeline Industries Guild for working with us and doing this as a joint event. I know that both of our organisations are putting on a load of webinars over the next coming period, so stay tuned to both our websites to get more information. And obviously we will be in touch with you all very soon. So thank you for attending and stay safe.
Thank you.
thank you all.
Thank you, guys.